Cool. Hello, everyone. Good evening. My name is Chi. I'm a principal researcher from Microsoft Research here at Redmond. It's great to meet folks in person. Today, I'm going to talk about this FLAML library and introduce some related products. FLAML is a lightweight library for finding models, accurate machine learning models efficiently, economically, and automatically. They can also be used for generic hyperparameter tuning purpose. The goal of this talk is to teach everyone how to use our tool in your work and make your life easier. I will provide code examples, demos, and lessons learned from customers. So no matter whether you have experience in AutoML or hyperparameter tuning before, I hope you can learn what can help you achieve in your daily job. So before we get started, I want to show you how to access the resources, especially some notebook examples. So if we click this link to GitHub repo, so let me move that to the screen. Yeah, so you can find our GitHub project page. There's a link to this hands-on tutorial at the KDD 2022. If you click that link, it brings you to a brief agenda, and there are a bunch of notebook examples you can find for different tasks. I hope you can try it on your laptop. So let's now get back. Oh, maybe one more thing is you can also find documentation page right here. Find more kind of examples, use cases. And there's also a page about the research we've done that you can find the publications reference there. Okay, let me switch back to the presentation. Yeah. Cool. So let's start from, go ahead, question. My voice, right? Yeah. Sorry about that. I'm having some trouble with my throat. I'll try my best. I'll start with some background introduction. A growing number of developers now have access to AI and machine learning techniques, and there's a strong interest of using them. The mission of our project is to help them master AI and machine learning operations. So to use machine learning in the application, we need to get the data from your application, prepare the data, and train models using the data and evaluate the models. Eventually, the models will be deployed and consumed as a software component. Before the models meet the deployment criteria, a model developer, for example, data scientist or machine learning engineer, keeps iterating the model training. There are a lot of decisions and choices to make for a general developer to find a good model. How can I move this button? Yes, breaking a bit. Okay, for example, they need to choose the right machine learning model, well implemented in a machine learning library to perform the training for their data and their tasks. There are many machine learning libraries like scikit-learn, XGBoost, LightGBM, PyTorch, transformers. Each of them offers many knobs to tune to optimize the model performance. For example, for LightGBM, which is a library for gradient boosted trees, we need to choose the number of estimators, number of leaves, learning rate, etc. When we use the wrong setting, we could easily see the accuracy drop from 90% to 50%, making the model unusable. Choosing the right combination of learner and hyperparameters for a new data set is really a trial and error process. Also remember, it's not just a one-time cost for one application. Every time the code, data, or deployment constraint, deployment criteria are updated, the choices could become invalid and the optimal configuration could change. And even with a huge effort of manual tuning, very often the decisions made are still not optimal, leaving performance gain opportunities on the table. Questions? No? Oh, sorry. Thought you have a question. But by the way, feel free to ask questions during my talk if you have any. Okay. So AutoML tools are built to automate that process, to remove the hassle of manual tuning for data scientists and engineers so that they can focus on other issues. And some of the tools empower developers without machine learning expertise. And we have seen a rapid growth in the AutoML software, including open source, cloud providers, and startup companies. The market size forecast in 2030 is about $15 billion. What kind of AutoML tools do users really need? Based on our interaction with customers, there are several important requirements they desire. For example, they desire tools to make them more productive with affordable cost. One common complaint of AutoML tools is they often consume large computational resources, especially on large-scale training data. That causes system failures, meaning the system is unable to return a usable model. Many users had to run experiments on limited computation resources, and they had to modify the model search space to reduce the total runtime. Some users would even revert to manual development, which is a big setback for productivity. Another important property is about customizability. On the one hand, it's necessary to provide enough customizability to target diverse requirements. On the other hand, if the tool requires too much effort in making many hard choices for users, it goes against the purpose of AutoML. Sometimes the user would say, I only want to customize one or two things, and I want the library to decide the rest for me. Most existing tools fail to meet all these requirements, so that we design FLAML, an open source library for AutoML and tuning. It provides the strives to be fast, economical, customizable, and extensible. We build a high performance and robust tuning layer, and then we build the AutoML layer transparently on top of it. The machine learning component uses existing machine learning libraries as black boxes. FLAML enables a smooth customization experience all the way from the most automatic AutoML experience to the more flexible tuning experience in the same library, covering all the middle grounds. For example, task-oriented AutoML is a high-level API suitable for all the users, no matter whether you're an expert or a beginner. It can be used as a scikit-learn style estimator in just 3 lines of code. It requires minimal input. You only need to specify the training data and the task type to use it. There are other scenarios where you want to use a lower level API to run generic hyperparameter tuning for fully customized function and search space. For example, when your machine learning task is not one of the built-in tasks, or when you need to directly optimize the performance for downstream application. In task-oriented AutoML, given a machine learning task and a particular resource budget, the goal is to find a model with the best performance within the provided resource budget without much manual effort. Here, a task is a machine learning task, including the training data and the task type. For example, regression, classification, etc. Classification and regression are the most common task types for tabular data. The data can be either NumPy array or a pandas data frame. We also support time series forecasting and natural language processing tasks. For time series forecasting and NLP tasks, there are additional requirements for the input data. For each task, there's a set of built-in estimators implemented in FLAML as the candidate machine learning estimators. The estimators are from popular machine learning library or deep learning libraries. So yeah, you can find some example notebooks to demonstrate how to perform this task-oriented AutoML in FLAML. If there's time in the end, I probably can use the time to demo a little bit. There are mainly 3 benefits of task-oriented AutoML. First, it can save manual efforts, including both the coding effort, like engineering effort, and the effort in manual repetitive tuning. And second, you can use small computational resource to find models with good performance. Extensive evaluation on the AutoML benchmark also verified the performance advantage of FLAML. These box plots show the performance difference between FLAML and several other libraries under different resource budget. A positive value means that FLAML is better than the comparative alternative. It's also worth mentioning that the prior AutoML solutions mostly rely on meta-learning to improve performance. Meta-learning tries to leverage tuning history on other data sets, and that requires evaluating certain performance metrics of many configurations of certain learners on many data sets as an expensive preparation step, and has limited customizability once it's done. FLAML can achieve better performance without meta-learning, which makes it possible to do flexible customization. That is another notable advantage of FLAML, because allowing easy and rich customization is helpful in scenarios where, due to business or deployment constraints, practitioners need to use a special machine learner, custom metrics, or certain constraint. FLAML is able to support these needs while maintaining performance advantage. I'll just use this picture to outline the system. Given a machine learning task and a particular resource budget, the goal is to find a model with best performance within the provided resource budget. So here, the task is a machine learning task, including the training data and the task type, and for example, regression and classification. And the components in blue are modules about AutoML, and the components in gray are modules about machine learning. The system performs multiple trials of tuning and model building within the specified resource budget. Each trial involves one step of learner selection and hyperparameter selection. Then, with the selected learner and hyperparameter configuration, it trains the model, evaluates the model on the validation dataset, and reports the validation loss. The hyperparameter optimization step is empowered by our cost-frugal hyperparameter optimization algorithm. By the way, FLAML does task and learner level data preprocessing, though the prevalent step is not shown in this figure. From the workflow of AutoML, we can see that in order to use AutoML, you need to frame the machine learning process in a scikit-learn fashion, which consists of a model training process via the fit function and the model inference process via the predict function. The final optimization metrics calculated based on the model's prediction quality on the validation dataset. But there are cases where the optimization metric can't be implemented in the customized metric function to do validation, or even if you could, the engineering cost would be too high. In such cases, it's more convenient to use this user-defined function to cover whatever procedures you want to include in your configuration evaluation process. For example, when the evaluation regarding the optimization metric relies on some downstream applications or data that can't be collected upfront. And sometimes some hyperparameters are not even about training models, but about how to use the models. And with the tune package in FLAML, you can easily include whatever you need in the user-defined function to achieve your goal. So more generally, it can be used even beyond tuning a machine learning model. We can tune generic hyperparameters for machine learning workflows, pipelines, algorithms such as reinforcement policies, mathematical statistical models like causal models, and so on. So far, our biggest success is in AutoML, but there are already use cases of FLAML beyond AutoML, which verifies general usability. It has a big potential in other fields. By the way, I mentioned that FLAML doesn't rely on the meta learning to achieve good performance, but if you do have resources to perform these expensive evaluations needed by meta learning, we offer a simple and effective meta learning approach in FLAML to further push down the AutoML cost. Instead of running full hyperparameter tuning from scratch every time, you can leverage the tuning experiences in similar tasks before. So for AutoML providers for a particular domain or organization, they can learn and customize defaults for users' tasks / learners / metrics based on their own tuning experiences. Based on meta learning, we built an interesting new feature called zero-shot AutoML. It offers a seamless way to leverage AutoML for commonly used classifiers and regressors, such as LargeGBM and XGBoost. For example, if you're using this LargeGBM.LGBM regressor as your current learner, all you need to do is to import the LGBM regressor from FLAML.default. Then you can use it just like the original GBM regressor. Your other code can remain unchanged. When you call the fit function from this new regressor, it will automatically instantiate a good data-dependent configuration for your tasks, which is expected to work better than the default configuration. So what's the benefit of zero-shot AutoML? The first benefit is that the online computational cost, that's the cost paid by the final consumer of AutoML. They only need to train one model. They get the hyperparameter configuration right away. There's no overhead to worry about. Another big benefit is that your code doesn't need to change. So if you currently have a workflow without the setup for tuning, you can use zero-shot AutoML without breaking that workflow. Our users find this zero-shot AutoML super easy to use in production, and as no code change is required to their existing production pipeline. So compared to tuning-based AutoML, zero-shot AutoML requires less input. For example, it doesn't need a tuning budget to be specified. A related benefit is that you don't need to worry about holding a subset of the training data for validation, which the tuning process might overfit. As there's no tuning, you can use all the training data for your training your model, and no need to worry about the reassembly strategy or data split, etc. So how does FLAML fit in the ecosystem? It works well with popular open source machine learning libraries like scikit-learn, PyTorch, Hugging Face, as well as cloud services like Azure ML. There are many internal and external use cases of FLAML, including both horizontal technologies and verticals. FLAML is shipped, for example, in Visual Studio and ML.NET to help .NET developers use machine learning in .NET applications. FLAML is integrated with popular MLOps infrastructure like MLflow and Ray. FLAML powers enterprise machine learning model building inside and outside Microsoft. In general, the impact of FLAML is in three folds: accuracy, productivity, and R&D. The models found by FLAML are successfully deployed in many products with high accuracy in different application domains like security, banks, marketing, civil engineering, supply chain, insurance, and healthcare. FLAML saves huge amounts of dev time for both developers and data scientists. The ability to conveniently incorporate the new algorithm into the existing pipeline, allowing easy extensions and being able to get large-scale parallel tuning makes FLAML plays a big role in R&D of some big enterprise customers. Is there any audience from the .NET world, like C# developers or .NET developer? No? So are you all Python developers? Okay, cool. Yeah, now just to briefly mention that the Microsoft offers multiple ways to do AutoML, and this is for example, the Visual Studio 2022 model builders for .NET developers. And besides model builder, there are also code-first approaches to AutoML with ML.NET and C#. Yeah, so I'll probably skip this part. Let's see. Before I conclude, before I go to the demo, let me just say that I'm also looking for collaborators to work on this open source project. There are multiple contribution opportunities you might be interested in. First, you can share your use cases and needs, especially the needs that are not well satisfied by our current features. And in this case, you are encouraged to connect with us on the Discord, and we can discuss what improvements are what improvement we can make. And second, you can also make development contribution to help improving existing features or help add new features, especially for the ones that you need. And for example, the zero-shot AutoML, time series forecasting, and online AutoML. And there are many new features and that are interesting, like support of computer vision tasks, a multi-model model, fair AutoML visualization and explanation, and also the most recent trend of generative models. And third, we can integrate with our other open source libraries as another type of contribution if it's interesting to you. we have successfully integrated Ray and MLflow with FLAML to help with parallelization, logging, and pipelines. And we're working on integration with Spark as well. And if you find some library especially useful in your workflow, you can consider implementing that, integrating them with FLAML. Yeah, so that's the last slide I have about the references. So do I have time for a short demo?
How long will it take?
It can be like 1 minute or 3 minutes.
Sure.
Yeah. Okay. It's however long that I'm allowed to. Yeah. And okay. Also, yeah, and on the audience interest. Let's see. I have a browser window right here. Yeah. Okay. Like I said, if we go to the tutorial page, let's go back. Try this one. Yeah, if you go to the third page, there are I just use one of them to demonstrate one particular use case for classification tasks. So yeah, due to time, I'm not going to run it online, but if you click the link here, open in Colab, it will open an interactive notebook experience, which you can run the notebook yourself. Yeah, so like all the notebooks, the first step is to install the FLAML package. Units pip install. So that's very easy. And after that, you can see this example. There are some data loading and pre-processing step. Here we are loading a data set from OpenML and do some pre-view of the data set. So once that data set is loaded, you got the training data. You can immediately start using FLAML with this AutoML package. You import this AutoML package, instantiate this AutoML object, specify some settings like time budget you want to allow, the metrics you want to optimize, the task type, and so on. And many of the options are optimal, so you could just use it without the settings as well. And then, yeah, so this is a core functionality. The fit function takes the input data and the settings and started to doing the tuning. You can see from the output, it will first output some information in the beginning and then start trying different learners. In this case, we have large GBM, random forest, cat boost, XGBoost, and so on and so forth. The first learner is large GBM, takes about 3 seconds to finish the first training and outputs its error. And in later rounds, it's tried a few number of times of large GBM and some XGBoost, GBM again, XGBoost, and so on. It will give you this status about what's the current best estimator and what's the best loss achieved by the estimator and so on. At the end, it will output what's the best model found. In this case, it's a large GBM classifier and what the hyperparameters are used. Then you can print out more information using this simple piece of code and find what's the best learner, configuration, best accuracy on validation data, training durations, and so on. Later on, you could pickle this object and use that later to do predictions. And we can validate on that performance on text data. You could also print out more metrics and check the log history and even plot this learning curve, etc. And yeah, I think that's the main demo to present. You can find more advanced information in the notebook, like how to customize learner, customize metrics, add your own learner, and how to do parallel tuning and so on. So we have plenty of content there online. You can find that. Yeah, I think that's all. Any question?
Yeah, we have a couple of minutes for Q&A.
I do have one question.
Yeah.
So I do have one question about the data preparation part.
Yeah.
So for example, my task is to identify the name of the animals in picture.
Yeah.
And my data resource is like maybe 10,000 pictures I downloaded from Google.
Yeah.
So during the process, does this library going to add some noise and also keep increasing the magnitude of noises during the process to find me the best model. Or
Add noises. What do you mean by add noises?
To add noise to those pictures, something like that. So for example, just like the first presentation we had. So for example, the magnitude of the noise is just I think it's 0.7%. It's not able to identify the pattern, right?
Yeah, I think that's a very interesting area about improving the model robustness, right, and making them more general and more robust to adversarial cases. We're actually doing some active research about how to improve the model robustness. We already found some ways. For example, we can use some special customized metric in the optimization to increase the generalization property. We haven't added that in the library, but we will do probably in the next version. And we also hope others with similar needs could work with us together. For example, join the Discord discussion and discuss your specific use case and maybe test these kind of new features in future. So we are very happy to work with you together on improving and adding these kind of features.
Okay.
Yeah.
I think my second small question is that you said it's just a limited budget, right? So does the model able to tell me, hey, with your limited budget, it's not going to give me a plausible or good model based on your limited budget with the confidence score I want.
Is the question whether the budget will be too small for
Does the library able to tell me, hey, your budget is too small. I'm not able to give you the model under your confidence level.
Yes, we do that. So in this particular example, so actually in every example, we will output the time taken to find the best model, as you see in this line, and also like how much budget it consumes. Like in this case, time taken to find the best model is 50% of the provided time budget. And it also says not all the estimators hyperparameter search converts. That consider increasing the time budget. So that's information you can see right there in that line. Go ahead.
We have one question online. You want to bring up the chat, please?
Oh, sure. So I think it's this
on
one.
the chat.
What type of data frames were passed in? Pandas data frame, yes. That's the data format we use. You can also use NumPy array. And in future, we are considering adding support for example, Spark data frames. Another question is any integration with array framework and array data sets. Yeah, so we have that's a very good question. We have been tightly integrated with the array system. For example, our distributed tuning and distributed AutoML functionality relies on the array backend to do parallelization. And FLAML is also already available as one of the tuning algorithm offered in array. So you can either use FLAML within array or use array within FLAML. So all of them are already done.
Okay, one more question.
But how much do you find that using the same parameters, the results change just for the time you use it, kind of the randomness of it? So you go through a training test and you have your set of parameters.
Yeah.
Sometimes you can do it and it ends up with one correctness. Another time you can do it and then it's different. How much do you find that can change in the testing you've done?
So are you talking about the case where the train data change or just one?
Just randomness means when you do one test and you run through the whole training set, you come up with an accuracy for that test.
Yeah.
If you run it again, depending on randomness.
The randomness. Okay, got it.
How much is that a factor in all this hyperparameter?
Yeah. Very good point. So this is about randomness in the training procedure. To make sure this temperature tuning is effective, we'd better control the randomness of the training to make it reproducible. For example, by setting the seed to fix the number. That has to be done carefully. So for most of the libraries we currently support, we already done that. recently find some bugs about some particular estimator that doesn't do that, but we're adding patches to fix those. Yeah, so after fixing these random seeds, the hyperparameter tuning will become more effective.